Welcome. In this video tutorial, we shall study the usage of uqFEM, that stands for Uncertainty Quantification Based Finite Element Methods. And this tool allows engineers to perform reliability-based structural analyses pertaining to natural hazards. uqFEM is developed at Sim Center at University of California, Berkeley. And Sim Center is focused on developing research and educational tools for a variety of numerical modeling purposes and simulations, especially relevant to natural hazards. Sim Center is the part of Natural Hazards Engineering Research Infrastructure, NARI, that is supported by National Science Foundation. Alright, so you can get the uqFEM from the Sim Center website by going to the Research Tools section. And once you have downloaded the uqFEM.zip, you can unzip it. And upon unzipping, you will see the following subfolders and files. So these are some subfolders that are essentially the template examples that come along with our application. There's a manual PDF that we provide and that explains the users how to essentially use this tool, and also contains a lot of installation and other details. uqFEM.exe is the actual application. If you double click on it, then the application is launched. There are additional supporting DLL files that you don't need to worry about, and those are essential to run uqFEM.exe. And there is an additional supporting Python script that is required by this uqFEM.exe. It's important to note that in order to run uqFEM.exe on your local machine, you will need to install softwares like Dakota, OpenSeas, and FeedPV. How to do them? It is all provided in this manual. However, if you don't want to do any installation, you can simply launch uqFEM.exe and you will be able to create an account on DesignSafe and run it on the cloud. Alright, so if you double click on the uqFEM.exe, you're going to launch the tool, and this is the window that appears upon launching the tool. You can go to the help section right over here and read more about the uqFEM tool. You can provide us the feedback, and if you click here, it will take you to the DesignSafe website where you can issue a ticket and submit in your issues, and we'll get back to you. You can read more about the version and license of uqFEM right over here. Alright, so this is the main window, and on the left side, you see over here essentially 4 modules that you need to work on in setting up your problem. You need to be able to specify which finite element method are you going to use. Currently, the uqFEM version 1.0.0 supports OpenSeas and FeedPV as its FEM methods. Additionally, you need to specify which uncertainty quantification method or optimization technique are you going to use for your analysis. You need to specify what are your input variables, their types, their bounds, and things like that. And finally, when you run a job and complete it, you can visualize your results in this section. Obviously, this is empty right now because you haven't run a job. You can run your job locally on your machine by clicking Run, but you need to make sure that all the relevant softwares like Dakota, FeedPV, and OpenSeas are installed. You can refer to the manual for more details. If you want to run your job on the DesignSafe cloud, you can click Run on DesignSafe. And before doing that, you must log in. And in order to log into DesignSafe cloud, you must register with the DesignSafe and send us an email for allowing you the access to the computational facility. Once your job is submitted and completed, you can get the results by clicking Get from DesignSafe. And obviously, if you press Exit, the uqFEM tool is shut down. Alright, so let's look at an example now. We go to File, Open, and try to load one of the default examples. In this case, we'll choose the example OpenSeas, and the template file is provided in this JSON object, test.json. So when we click on it, our example is essentially loaded. So in this example, we are essentially interested in studying the structural response of a truss that has got uncertainty in its elastic modulus, in its cross-sectional area, of the bars and the applied load. This is going to use OpenSees, and it is assumed that the user is familiar with the working of OpenSees finite element software. Since this is gathering a stochastic response, we are going to use a sampling method, and in particular it'll be a Latin hypercube sampling method used from Dakota. For this purpose, we are only going to choose 100 samples, and it is a random seed 981. We are generating and aggregating our structural response on the nodal displacement variable. In terms of the input variables, as stated before, we have variation in the elastic modulus and the applied load and the cross-sectional area of the bars, and all these are modeled using a Gaussian distribution with a mean and standard deviation. This corresponds to example 1 in the manual, and you can always choose a different probability distribution function as available over here, but we'll stick with normal right now. To simply run this job on a local machine, we go and press run, and the job essentially gets launched on the local machine. Now we can go to the results section over here, and essentially we have completed our job. Over here we see a summary of the result, where the output variable, that is the nodal displacement, it has a mean of -7.5 and a standard deviation of 1.3 units. These are more detailed results that are being projected here from the outcome of Dakota runs. One can look into it in detail, and these are some plots of the nodal point displacement corresponding to our different 100 samples, and this is displayed in form of a table here. Alright, so let's look at the next example. Here we are going to look at the parameter estimation using optimization methods. So I'll go to the example and calibration, and again the information of my example is all stored in form of a JSON object, so I can select this file and essentially load my example. So this problem is essentially concerned with the parameter estimation for a 3-story frame that is subject to harmonic ground motion. Our model consists of two unknown parameters. Those are damping ratio and factor for the weight to the roof of the structure. And we want to find the optimal values of these two parameters so that the structural response matches with the desired or the target response. Again, I'm going to use OpenSees for this example. In the method selection, we are going to use an optimization method based on Gauss-Newton with a total of 1000 iterations and a convergence tolerance of 0.01. The response parameters are essentially the predictions from our finite element simulation, and we want to match them closely with the target values that we have also provided. Input variables, as mentioned, are the roof factor and the damp ratio. Here they are treated as continuous variables with a lower and the upper bound and an initial point to start the optimization. Now we are ready to go, and we press run. Our method is running, and we have essentially done a parameter estimation problem and obtained roof factor of 0.774994 and a damp ratio of 0.34992, and this, according to this optimization run, gives us the least error. Alright, so let's look at more details. So we have got the best parameters. Our residual is pretty good, of the order of 10 to the power -3, and we have a fairly high confidence on the parameters that we have estimated. Finally, here are some direct convergence plots, and this shows the response of the structure, how the error is essentially decaying, and within few iterations of Gauss-Newton method we get the optima. So you can see here the response, essentially the error in the response is essentially tending to 0. Okay, in this illustration we are going to use uqFEM on the Design Safe cloud, and in this example we are going to use FreePV as the finite element solver. So for this purpose, I'm going to go to File, Open, select the example FEP, and then load my problem by selecting this JSON object. So as you can see, all the fields are now populated, and this example essentially corresponds to example 1 problem itself. The only difference being that now we are using the FEP-PV as the finite element solver. And again, in the method selection, we are using the Latin hypercube sampling method of Dakota. Okay, so in order to run this example on Design Safe Cloud, I need to first log in. So I would go here and type my user ID and the password. And click login. Okay, so now it says login success. And then all I need to do essentially is click run on Design Safe. So when I click run on Design Safe, it'll ask me for a job name. So I just put test FEP. I'll choose 1 nodes, let's say 8 processors, and simply submit. So now you can see the status of the files being transferred to the Design Safe Cloud, and then the job is going to get submitted. So now you can see that the job has been started successfully, and in order to get the status of the job, I simply go and click on Get from Design Safe. When I click here, I get a bunch of status for my different jobs that I submitted in the past, and currently I submitted this test underscore FEP. Due to server being busy, it still shows in the queue right now, and if I return back after some time, the job should be finished. Alright, so I get back here and see that my job has been finished, and I simply right click and retrieve my data. So as you can see that data is being fetched from the Design Safe Cloud, and there you go. Here I get the pretty much the same result that I got using OpenSeas. So I won't go into details, and that's pretty much about the uqFEM version 1.00. Thank you.